All right, so as promised, here's a definition of a new proposition that uses this idea. The existence of a bijection, f from A to B, is going to be expressed like this. A wiggly equals B. So it's not equality. It's not saying A is a subset of B or B is a subset of A. It's just we're defining this proposition to mean there exists a bijection. And we're also going to say, so usually we read this out loud as A has the same number of elements as B, or A has the same cardinality as B. So you could read this as saying A has the same cardinality as B. There's some quality that A and B share, and for which the fact that they share this quality can be expressed like this, by the existence of a bijection, and that quality is called cardinality. We also define this short way of saying A has fewer elements or equal to the number of elements of B, or maybe B has at least as many elements as A. We say it like this. So this is what it means. That means if you want to prove things about this, then you have to use the definition. You cannot just, count elements with your finger, right? You need to use the definitions to prove things. So we think of this as meaning B has at least as many elements as A, but this is what it actually means. Whatever this entails, this is what it means. That there's an injection. All right, so I guess it takes some time working with these to be really convinced that when you define things this way, this is a way of saying that A has as many elements as B, or this is a way of saying B has at least as many elements as A. You really have to work with them. But I hope the previous segment showed that it's plausible at least. Notice that we never really have to mention natural numbers in this picture. We just studied the natural numbers, right? So if I told you, I'm going to define what it means for B to have at least as many elements as A, you would expect me to write down some inequality involving natural numbers, maybe, where one natural number represents how many elements B has, and one represents how many elements A has, and I'm comparing them by an inequality. But I'm not doing that. Natural numbers don't show up here. We could have made these definitions before we defined the numbers. So numbers are not needed to talk about having the same number of elements as another set, or having at least as many elements as another set. You don't need numbers. I think that's really interesting that you don't need numbers to talk about this. And it's pretty important because it means you can discuss these ideas without knowing that there's that a set has only finitely many elements necessarily. So these ideas work for infinite sets, whatever that means. We haven't defined that yet, but these ideas work for infinite sets perfectly fine. I guess the first thing you want to know about these is like this wiggly equal sign has certain properties that you would expect of it if it's going to be anything similar to an equal sign. So if the wiggly equal sign, A has the same cardinality as B, is really to represent the fact that there's some quality that A and B share, namely number of elements, whatever that means. But if this is really to represent the fact, if this is really representing the idea that A and B share some quality we call cardinality, then it should function like equality in certain ways. So it should be symmetric in the way equality is symmetric, because if there's this thing called cardinality, this feature of sets called cardinality, such that this statement says that A and B have the same of that thing, have the same cardinality, then that should be the same as saying B and A have the same cardinality. So this should be provable, and that is theorem 115, or at least part of it. And there's also that's 115.2. And there's also 115.1, which says that things have the same cardinality as themselves. And 115.3, which is transitivity. If A and B have the same cardinality, and B and C have the same cardinality, then A and C have the same cardinality. So let's prove that one. And the rest I'll leave as homework, possibly. So let's prove that last one. It's transitivity. So that would be theorem 115.3. Let me just say proof of. So I can get started with the proof right away. Assume A wiggly equals B and B wiggly equals C. And my goal is to prove that A has the same cardinality as C. So let me try to unpack what I have. The fact that A has the same cardinality as B means there's a bijection from A to B. So that means I can get one. There exists one, so I can get a bijection. Or I can say, let F be a bijection from A to B. The fact that B and C have the same cardinality implies that there's a bijection from B to C, so I can get one. And I should not give it the same name, right? That's the classic mistake with existential instantiation, when you give your new variable a name that conflicts with older variables. So we know there's a bijection A to B, and we know there's a bijection B to C. Those are separate existence statements. Okay, so I think I've fully unpacked what I have. I mean, I can unpack further by writing down the definition of bijection, or the definition of F maps A to B or G maps B to C, but I don't know which aspects of those definitions I need to use. So I'll stop here and think about my goal. My goal is to show that A wiggly equals C, or A has the same cardinality as C. That means I need to show that there exists a bijection from A to C. I have a function from A to B, and I have a function from B to C. Do I have a way of building a function from A to C? And also, can I make sure that I do it so that it's a bijection? Well, this is sort of screaming at you, please use composition, right? F and G really want to be composed together. So then G composed with F maps A to C. So why is that? That's the essence of composition theorem. So let's actually put down some theorem numbers. That one is theorem 63.2. And G compose F is bijective. Why is that? How do I know that composing two bijective functions is bijective? Well, hopefully this reminds you of a homework problem that you have done. This is part of it. So the homework problem was to prove theorem 78, and this is 78.5. That the composition of two bijections is a bijection. All right, and that's it. Since we have found a bijection from A to C, we can conclude that A wiggle C.